Okay, my dear students, this is the second part of the lecture. Uh, we will today discuss the impurity conductivity, in which you will see that how the semiconductors are so useful. Certain impurities and imperfections drastically affect the electrical properties of a semiconductor. The addition of boron to silicon in the properties of one boron atom in the proportion of one boron atom to 10 to the power 5 silicon atoms increases the conductivity of pure silicon at room temperature by a factor of 10 to the power 3. So you see that if you just add one boron atom to 10 to the power 5 silicon atoms, the conductivity increases by thousands times. So very interesting and very useful. In a compound semiconductor, a stoichiometric deficiency of one constituent will act as an impurity. Such semiconductors are known as deficit semiconductors. The deliberate addition of impurities to semiconductors is called doping. So these are the two types of impurities which can increase the conductivity of the semiconductor considerably. We consider the effect of impurities in silicon and germanium. These elements crystallize in the diamond structure. Each atom forms 4 covalent bonds, one with each of its nearest neighbors, corresponding to the chemical valence for 4. If an impurity atom of valence 5, such as phosphorus or arsenic or antimony, is substituted in the lattice in place of a normal atom, there will be one valence electron from the impurity atom left over after the 4 covalent bonds are established with the nearest neighbors. That is, after the impurity atom has been accommodated in the structure with a little disturbance as possible. Impurity atoms that can give up an electron are called donors. So we have donor states. The question is that where should we place the energy level of a donor? The structure in figure 19, so this is the figure. So we have all the silicon atoms covalently bonded with the nearest 4 silicon atoms, but now we have added a arsenic impurity. So there is just one arsenic atom in the neighborhood, and we will see that this, let's see, the extra electron moves in the Coulomb potential E over epsilon r of the impurity ion, where epsilon in a covalent crystal is the static dielectric constant of the medium. The factor 1 over epsilon takes account of the reduction in the Coulomb force between charges caused by the electronic polarization of the medium. This treatment is valid for orbits large in comparison with the distance between the atoms, and for slow motions of the electron such that the orbital frequency is low in comparison with the frequency omega g corresponding to the energy gap. So these conditions are satisfied quite well in germanium and silicon by the donor electron of phosphorus, arsenic or antimony. We estimate the ionization energy of the donor impurity by using the hydrogen theory The Bohr theory of the hydrogen atom may be modified to take into account the dielectric constant of the medium and the effective mass of an electron in the periodic potential of the crystal. The ionization energy of atomic hydrogen is minus E square m over 2 h cut square in CGS units and minus E4 m over 2 into 4 pi epsilon naught h cut square in SI units. So this we have taken from the theory of hydrogen atoms. In the semiconductor with dielectric constant epsilon, we replace E square by E square over epsilon and m by the effective mass me to obtain equation 51 as the donor ionization energy of the semiconductor. The Bohr radius of the ground state of hydrogen atom, as taken from the theory of hydrogen atoms, is 4 pi epsilon naught h cut square over me to the E square in SI units. The Bohr radius of the donor is given by equation 52 here. The application of impurity state theory to germanium and silicon is complicated by the n-isotropic effective mass of the conduction electrons, but the dielectric constant has the more important effect on the donor energy because it enters as the square, whereas the effective mass enters only as the first power. To obtain a general impression of the impurity levels, we use the effective mass approximately equal to 0.1 of the free electron mass m for electrons in germanium and me as 0.2 m in silicon. The static dielectric constant is given in table 4 somewhere here. This is the table 4 where you can see the values of epsilon. The ionization energy of the free hydrogen atom is 13.6 electron volts. So for germanium, the donor ionization energy ED on our model is 5 milli electron volts, reduced with respect to the hydrogen by the factor equal to 4 into 10 to the power minus 4. The corresponding result for silicon is 20 milli electron volts. Calculations using the correct n-isotropic mass tensor predict 9.05 million electron volts for germanium and 29.8 million electron volt for silicon. Observed values of the donor ionization energies in silicon and germanium are given in table 5. This is the table 5. The radius of the first Bohr orbit is increased by this factor over the value of 0.53 angstroms for the free hydrogen atom. The corresponding radius is 80 angstroms in germanium and 30 angstroms in silicon. These are large radii so that donor orbits overlap at relatively low donor concentrations compared to the number of host atoms. With appreciable orbit overlap, an impurity band is formed from the donor states. The semiconductor can conduct in the impurity band by electrons hopping from one donor to another donor. Okay, so we have acceptor states and we have the donor states. A hole may be bound to a trivalent impurity in germanium or silicon, just as an electron is bound to pentavalent impurity. Okay, so we have, you can go through the description given here, and I just wanted to point out that by adding the donor impurities or the acceptor impurities or both, we can increase the conductivity level of a pure semiconductor. So such semiconductors are known as the extrinsic semiconductor, and the impurity is the impurity conductivity, and the conductivity is the impurity conductivity. The number of holes and electrons are equal in intrinsic regime, as we read before, but now by adding the impurities we have unbalanced this thing, that the intrinsic electron concentration is at 300 degrees Kelvin is about 1.7 10 to the power 13 cubic centimeter in germanium and 4.6 into 10 to the power 9 cubic centimeter per cubic centimeter in silicon. The electrical resistivity of intrinsic materials is 43 ohm into centimeter for germanium and 2.6 into 10 to the power 5 ohm centimeter for silicon. Germanium has 4.42 into 10 to the power 22 atoms per cubic centimeter. The purification of germanium has carried further than any other elements the concentration of the common electrical active impurities. Okay, you go through this rest of this paragraph. The thermal ionization of donor and acceptors. The calculation of the equilibrium concentration of conduction electrons from ionized donors is identical with the standard calculations in statistical mechanics of the thermal ionization of hydrogen atoms. If there are no acceptor present, the result in the low temperature limit is given by this. So this is the concentration of the electrons and you given by equation 53, and you can also go through the rest part of this paragraph. So that completes our discussion on this chapter on semiconductors. You must go through the summary at the end of this chapter given at page 217, and also you must look at the problems. I would suggest you to solve problem number 1 and problem number 2 from this list. You can easily do these problems by using the formulae developed in the theory of this chapter. Okay, that's all for today's lecture, and we have completed the chapter on semiconductor physics. In the next lecture we will start a new chapter and a new topic. Okay, thank you very much.